Hello, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain, and before I introduce David Lewis, who is the most recent addition to our engineering staff, as we are wading into this highly anticipated presentation on grounding analysis, I'd like to start with some poll questions as we are of a mind to do. Again, your participation is requested. There's no obligation, but it does help us kind of center the discussion. Let's start with how many grounding studies a year does your company generate or conduct? Again, we'd like to take a sampling of the audience just for general information purposes. We do appreciate your attendance today and your support of EasyPower. So it looks like we got a quorum here. Let's give this another 5 seconds. All right, and here's how folks have weighed in on this one. Looks like we have a fairly good representation of the audience, if you will. And our second question is, which software or tools are you most familiar with, at least from the list? And this is an area where the field is not nearly as competitive as some other areas, and why we're excited about our association with XGS Labs. So we'll give this another 5 seconds. And here's how people have weighed in on this one. All right, thank you. And then finally, of the studies that you do, which area of the analysis gives you the most issues? And this is our first presentation on the topic this year. And I think based upon the response that we're getting, we'll probably have others in the near future. So again, thank you very much for attending. Just as a side note, we have recorded David's presentation so he can be online answering questions real time, and we will have a Q&A session at the tail end. So again, thank you for attending. Here's how folks weighed in on this last question. We do appreciate your support of EasyPower. So with that, let me hand this off to David Lewis.
Thank you, Jim. As stated, my name is David Lewis and I work with EasyPower. And today I am presenting the grounding analysis for utility scale photovoltaic power plants. So the purpose of this presentation is to outline a methodology for a grounding system analysis of large scale, utility scale photovoltaic systems. When we're talking about this today, I'll be using terms and concepts from the IEEE Standard 80, which is the substation grounding standard. At the end of this presentation, it's my hope that you'll be able to describe a typical solar power plant grounding layout, identify the challenges encountered when evaluating a solar power plant grounding system, and describe analysis techniques to accurately assess a grounding system. To achieve those goals, we're going to talk about what a utility scale photovoltaic power plant is. Then we'll go into a little bit of the grounding basics just so everyone's familiar with the terms and definitions. Then talk about the photovoltaic power plant grounding system and the challenges associated with doing an analysis for those. And at the end, have a case example to demonstrate some of the topics we discussed in this webinar. So I'm sure all of you have probably seen some photovoltaic panels on residence or commercial buildings in your area. What these do is that they convert solar energy and take that and convert it into a DC power. That DC power is inverted into an AC power to be used by the residence or commercial building itself. So if we take that concept and just make it much, much larger, we end up with a utility scale photovoltaic power plant. These systems can be really large, often covering several acres. And when we talk about a utility scale photovoltaic power plant, we are usually referring to a system that's 5 megawatts or larger. In this presentation, the systems we're typically talking about something that's are challenges that are associated with 50, 100, or 200 megawatts or larger. As you go up in your power generation, you have much larger area that you take up for those solar panels. Before I go to the next slide, I want to point everyone over to this little open space between the solar panels. This is a visual of one of the inverters. So here we have the solar power plant as a one line. We have our PV panels on the right, and these are connected at the inverter and then converted into an AC power, and that AC power is often stepped up to a medium voltage. That medium voltage could be transferred back to the grid at an existing utility station, or often with these larger 50, 100 megawatt solar power plants, they could have their own collector substation. And that substation could convert that medium voltage into a high voltage for transmission back to the grid. One thing to note is that this inverter and the string of PV panels could be anywhere from 1 megawatt to 5 megawatts. And I would anticipate as technology improves, we could see that increasing to ever larger strings of panels. So let's talk about some of the grounding basics before we get into a photovoltaic grounding system. So why are we doing grounding? One, it allows proper equipment operation in normal and fault conditions. It also provides surge and lightning protection. And this last bullet point, the personnel protection under fault conditions, this is primarily what we are considering when we're doing a grounding system analysis. Some of the definitions with a grounding system analysis, one of them is your earth or ground current. This is the current that's going through your grounding system and returning to its source through the earth. What that does is it creates a ground potential rise. And I think that's well illustrated by the image on the right here. This is the electric potential that's developed at your ground grid in that surrounding soil. And it's really the voltage difference from your ground grid to some remote point or remote earth, we'll call it, a location where there's zero potential. It's important to note when you get to much larger systems that your ground potential rise that you generate from a fault is dependent upon the injection point, which is very pertinent for our discussion of these large photovoltaic power plants today. So when we're thinking grounding and personnel protection, we're primarily looking at two criteria, our touch voltages and our step voltages. On the left is a little demonstration of what a touch voltage concern would look like. We have a fault occur and the grounded equipment in a station is elevated to 1,000 volts. An individual is touching one component of this system and their feet are at a different voltage potential from that ground potential rise. So in this example, the individual has 1,000 volts at their hand and 800 at their feet. So there's a total of a 200 volt difference. That is the 200 volt touch voltage. On the right is a demonstration of what a step voltage is. We don't necessarily need, well, for a step voltage, we're not actually touching any equipment. It's simply the difference in potential from one foot to the other based on the individual's stride or their step. So that ground potential rise drops off in the soil and you have various gradients. And because of that, you can have a voltage difference between one foot and the other. This example, the individual has 900 volts on one foot and 800 volts on the other. So they have a total difference of 100 volts, and that would be a step voltage of 100. So now we're familiar with some of the definitions of a grounding analysis. Let's look at an example of a photovoltaic power plant grounding system. Here is an example of a unified system where our PV arrays are all contained within one area, surrounded by this perimeter fence. With solar power generation, it's very flexible for these PV systems to be fragmented, and you could have a more segmented system or multiple individual generation areas. So On the bottom here of this larger photovoltaic power plant is our collector substation grounding system. This has a typical grounding layout. Usually each of these grid spacings is more in the 10 to 50 foot range and is often connected to the solar power plant grounding system. When we look at the solar power plant, we have these very large squares, and contained in these are the solar panels themselves. These are much, much larger areas, and they could be anywhere from 100 to 800 feet, and they overall can take up an area anywhere from half a mile to a mile or more as far as the one point of the system to another. Then inside these very large areas, you have a much smaller ground loop. This is usually where the inverter is placed, and that inverter equipment is going to have its own independent ground loop. So one of the pros of having such a very large system is that it reduces your grounding system impedance, which results typically in a lower ground potential rise. That said, this is a very sparse layout. There's not a lot of conductor out here, as opposed to in the collector substation. You have a lot faster drop off of your ground potential rise. So let's go into some of the challenges associated with a photovoltaic power plant system. One is just data acquisition, understanding the soil characteristics and getting your fault data and coordination data. Another challenge is understanding the physical and electrical system. This requires a lot of information from often various sources. And another challenge is the software's capability. Because of how large these systems are, it's very easy to find the limits of a given software system for grounding analysis. So let's first talk about soil characteristics. Because of these systems being so large, you often have variation from one point to another as far as the soil's electrical characteristics. This is typically limited to the upper soil layers. So in order to work around this, it's recommended that several short traverses be taken. And an example of this is that we can take multiple measurements in each of these areas where we anticipate having the solar panels and get an understanding of how the soil resistivity changes or remains the same across one point of the site to another. Another challenge is characterizing the deep soil layer electrical characteristics. If we are following the recommendations from, for example, IEEE Standard 80, we want to be able to perform a winter soil resistivity measurement with an A spacing on the order of the system that we are analyzing. If my solar power plant is 1 mile wide, it could be very challenging to have a winter resistivity measurement that's 3 miles long. Really, what we want to do is be able to take the measurements as long as we can to give the grounding analysis the best information that we can. Another thing while we're talking about soil characteristics, inside the solar site, we typically don't have any sort of gravel or crushed rock surfacing. This is really just a cost prohibitive type of measure. Most substations, you'll find this gravel crushed rock surfacing, and it adds a resistive layer and helps with evaluating that personnel touch and step voltages. We can't really do that for a site that covers multiple acres. So next, we'll talk about our fault coordination data. We really need to have the utility information, understanding how much of the fault could be provided by the utility, as well as understanding the protective system that they're going to be implementing from the utility to the solar site. If this is a large station or a large solar site, it'll often have a collector substation with its own transformer and breakers, and we need to understand what the protective systems are at the substation and along the feeders in order to determine proper clearing times, as well as understand the possible sources for fault currents. And when I talk about that, in a grounding analysis, if you have a local source for a fault, that local source, the current from that local source is going to return upon metallic components instead of going through the earth and contributing to a ground potential rise.
In a large site with a collector substation, the transformer is going to be a somewhat local source of fault current as it has a direct metallic connection. We can model the current to account for the fault returning to its source through the metallic components as well as through the soil.
Now we also need to understand a lot of details about how the solar power plant is connected. We need to understand if the PV arrays are grounded, if they're using a continuous conductor adjacent to the panels, or if they're anticipating that the panel track itself is going to act as the ground. On the image on the top right, we can see there is a conductor that's joining one piece of the track to another support post. So this is indicative that for this site, they're using that panel track as their grounding connection. Another option is that they may have ground connections at each of the support posts. This is all important information to know as far as what is physically grounded and what could be a touch potential issue. But it's also important to note as we could use or think of the support posts instead of as a physical system just supporting the PV arrays, it's also similar to a ground rod. So we could consider this almost as if it's a auxiliary grounding system. And we'll get to that in our case study. If we're thinking about the touch potentials to these panels, we also have to consider the PV panel span and how far away they are from the individual post or its nearest grounded point. The image on the bottom shows an individual touching the edge of the PV array. Those panels can extend 3 feet, 6 feet, 9 feet from the posts. So an individual may be susceptible to a touch voltage, not just based off how far they can reach, but how far they can reach and how far those PV panels extend away from the posts. If you're doing an analysis that has a collector substation, it's important to note if that substation is directly connected to the plant. If it is, you may also have an option to consider neutral or shield wires, and I would recommend that we actually model those. Depending on the location of the fault, the impedance to the connection where the neutral shield wires are can change. And so actually modeling that gives you a more accurate assessment for how much fault will go into your ground system locally and how much will take an alternative path through that neutral or shield wires. Next on the software limitations, you really cannot do these types of large systems with a grounding analysis that assumes equipotential system. It is common to have that for a smaller substation application where there's a tighter mesh. But as you can see on the image below, there is a significant ground potential rise at one corner of the site, and that drops off significantly and almost is non-existent on the other corner of the system. Your analysis must be able to account for the self and mutual impedances to accurately account for the physics of a fault occurring at your solar site. And as I mentioned before, we should be taking advantage of the local sources. In order to do that accurately, we should model that with multiple sources or multiple energized conductors. Another requirement for your grounding software is that it has to be able to accurately model the soil as you've measured it for your system. Whether that requires you be able to analyze 3 layers, 5 layers, 10 layers of soil, probably not 10 layers, but you need to be able to consider that, or maybe it's just multi-zone analysis. It really depends on what your soil resistivity information dictates is necessary for an accurate analysis. With these very large systems, you can often overcome or overwhelm your actual computation capability as well. Possibly it's the software that's limiting your analysis ability. Possibly it's your actual computer can only have so much RAM and CPU able to do the calculations for you. Either way, you need to understand if your software is limited in one way or another and try to approximate or overcome that with your best engineering judgment. So now that I've understood my soil characteristics, I have a grasp of the fault magnitude and clearing times, and I understand where my limitations or where I may need to implement some engineering judgment based off my software limitations, we can start determining some hazardous scenarios. What I'm typically looking at are considering where my fault magnitudes and my grounding geometry are going to make touch and step voltages the worst. I'm also considering my touch and step voltage criteria, thinking about my soil characteristics and clearing time, what's going to make those limits much less and make my grounding analysis more challenging. Before I go into the case study, I want to mention a couple additional thoughts, I guess. One of those is your perimeter fence. Many of these sites have a perimeter fence to add some physical security. However, we should be concerned about transferring voltages to that perimeter fence. If you are directly grounding your perimeter fence, it's not recommended to run a grounding conductor from your PV site or your collector substation to the perimeter fence, and that often can contribute to a transfer voltage issue or create more hazardous touch potentials on the perimeter fence. If you're adding your own independent grounding system on that perimeter fence, you should be cognizant that you're not picking up some of the voltages that could occur from your ground potential rise of a fault at your site and creating transfer voltage on the perimeter fence. We kind of mentioned this before on fault current split, considering our shield wires or neutral wires as an alternative path for fault current to flow. It's best to model those systems as your impedance to that connection can change depending on where that fault occurs. Another note, when you are validating the software analysis and validating the engineering work with field testing, the field testing can be extremely complex and challenging. You may need very large or powerful equipment or extremely sensitive equipment because of how large these systems are. You also need to have personnel that are knowledgeable and able to work around with more complex situations. So let's get into the case study. So for this study, or this case example, we have different soil characteristics depending on the region. So on the left, we have a zone 1, which is 75 ohm meter with a 48 ohm meter bottom soil layer. And you'll notice each of the different zones has the same bottom soil layer because of the soil measurements were indicative that that was consistent across the site. I'm looking at various fault conditions, typically one at a time. So I am looking at a fault occurring at my northwest corner, my northeast corner, at the collector substation, and that may provide the largest ground potential rise and contribute to a touch or step voltage hazard in my site. I'm looking at where the largest fault occurs within my site as well, and considering fault current clearing times. So first, let's take a look at the fault in the northwest corner. Here, I have my fault current injected into the grounding system. At the substation, I have another current, which is the local contribution that it's 180 degrees out of phase, and I'm pulling that fault out from contributing to a ground potential rise. Here's the metallic potential of a fault in that corner, and I want to direct your eye to this little point where we can see that the perimeter fence is actually experiencing some transferred voltage. Whether or not that is sufficient to create a hazardous scenario should be assessed as a part of these types of studies. So here's our permissible touch and step voltage plot. Just to define some of this, the green areas represent areas where my touch voltages and my step voltages are meeting acceptable limits. The yellow areas represent locations where my touch voltages is exceeded if there's equipment. I know that in this large yellow area, I have several PV arrays, and all of those panels are indicating that if somebody's there and working on the panel, particularly cleaning it off from the dust or whatever may collect on the panels, they could be susceptible to a hazardous touch voltage. One way to work around that is considering our auxiliary grounding system. Those posts are acting as several ground rods. And what they do is that they reduce the ground potential rise in that area, and they also reduce how quickly that ground potential rise drops off. Here's a plot of the ground potential rise. Before we model the panel array posts, you can see that the ground potential rise drops off relatively quickly from 2,560 volts. Now, when we model in the PV array posts, not only does the ground potential rise, the overall magnitude reduce, but the gradient, the voltage difference from one part of this to the other, reduces at a much lower rate. You can see that when I'm looking at a fault in the central location. This is the location with the highest fault current magnitude in the PV site. We can see we go from a system that appears to be non-compliant for touch voltages to relatively mostly compliant for touch voltages and step voltages by the PV arrays, indicated by the green area here. Now let's look at the northwest corner, or the northeast corner, excuse me. So this location actually has the lowest fault current magnitude, but it has a little bit longer clearing time. It also had some of the worst soil characteristics, if you remember from a few slides earlier. So here we can see our plot is indicating that we're not meeting our touch voltage criteria in areas where we know our PV panels are located. When we model in those support posts, the auxiliary grounding system we'll call it, we see improvement, but we're not meeting compliance for our touch voltage criteria, especially along this left edge here and on the right edge. So you can't really assume that when you model in your PV posts that you're going to be compliant. I just wanted to make sure that people understand that. We're looking at these as an auxiliary grounding system, but we still need to evaluate to make sure that we're actually performing the study to determine what's necessary for touch and step voltage compliance. In this situation, we need to add some additional grounding conductor in the northeast corner. So an additional conductor loop closing the open space on the right side here, and then a little bit tighter grid spacing on the left side here. So I would like to, before I open up to questions, that if you have any thoughts after this webinar, feel free to email me or check out our website at easypower.com. We have some videos demonstrating the XGS Lab software. At this time, I'll go ahead and open up to questions.
See, so one of the questions that came up is that in some designs, they have an isolation between the DC and the AC side of the inverter. Often these utility scale photovoltaic systems, we'll see that they are grounding the metallic components of the site, which would include the track array. So in those situations, we would see this kind of larger grounding system. Also kind of entailed in that, where your fault current source is coming from dictates whether or not there will be a ground potential rise associated with that, and then inherent touch and step safety issues. And I guess one other thing I kind of wanted to mention too in this presentation is that the approach shown here is one methodology for performing a grounding system analysis for these large photovoltaic systems. There are various approaches. So mine was modeling those auxiliary grounding systems, those solar posts, as high density in the areas that I'm looking in. You can approximate other portions of the system using lumped impedances, or you can model the entire system entirely if your software is able to do that. So another question is how long these models can take. It really depends on how many components you put into your system. For XGS Lab, the ones that I was running, it could take about 20 or 30 minutes to run the case and then get the plots in 20 or 30 minutes as well, as far as the touch and step plots. That said, the next version of XGS Lab should be about 4 times faster on the touch and step plots. Another individual asked, if you're starting to hit up against your software's capabilities as far as how many elements you can model, you can start reducing the density of those auxiliary grounding systems
to lighten the load or the computational load. That's one way to approximate it, and it generally should result in a more conservative analysis because you're reducing the amount of grounding system that's in your model. And just to clarify, this is the XGS Lab grounding software that's used for the analysis. Just so people are aware, EasyPower and Cint Engineering have partnered. So EasyPower is providing the XGS Lab software in North America. So if you guys have any questions regarding that, please feel free to email us or also check out the website where there's more videos on the use of the XGS Lab software. So I'll try and get to as many questions as I can through this. They are coming in rather quickly, so I may have to answer some of the questions via email later, but try and get through as many of these as possible. Another question is, can the plots be imported from AutoCAD or other CAD software? XGS Lab, this model was actually imported from a CAD DXF, and it can be exported back out to a DXF. So you're able to do that, and you can export the contour plots. For example, your touch or step voltages, you can model them or get the results in contours instead of colors, and you can export those lines into your DXF. Oh, another person actually had a good question of how I actually am modeling this system. So let me just zoom in here. What I am doing for both my fence and my tracker array posts, my PV posts, I am modeling based off the dimensions of the I-beam that supports the PV panels, and that's modeled as a steel conductor going into the soil, the depth of the PV post depth. And then each of them are connected by a fully insulated conductor as this system's modeling a system that's connected via the above grade tracker system or the tracking system. So the supports. So that's how this model was built. And that's highly similar to how I've done my fencing, is that it's a steel fence post that is modeled in the soil at a depth of approximately the depth of almost 3 feet, probably like 2.5 feet, with an insulated conductor between the two. So someone asked about the characteristics of concrete and how that could affect the characteristics of this post as they may be embedded in concrete. Typically, when you are installing the posts and then pouring concrete in there, the concrete takes on a lot of the soil characteristics of its surrounding soil because it matches the water content of the soil. So you don't really see a large difference or significant difference when you have a direct embedded fence post versus a concrete encased fence post. There is a difference though if that is a concrete that's kiln dried, in which case that typically maintains a high resistivity. So I'm going to go ahead and show the fault current that I injected for this system, just so people can see what that looks like in my actual model. A couple questions were brought up asking that. So I'm going into my conductor properties, and I have my, let's say, 17,000 amps that's inserted at this point if insulation or something were to fail on one of the conductors, or if personnel accidentally created a fault condition. And then at my substation, I'm pulling that out with a current that's 180 degrees out of phase with the current that I was injecting into my system. And someone asked if it's possible to model this system without direct connection of conductors. And absolutely, I think the software that you need in order to do these type of studies has to be able to evaluate components that are not directly connected when you are really considering the transfer voltage to a perimeter fence. That's essential to be able to do that.
David, we're going to post a copy of this webinar on the website, and we'll include a list of Q&As that everybody's responded or submitted, and people can download it if they'd like.
That'd be good. I think I'll probably take one more question here before responding to the remainder through email. But one of them was asking about the system testing for this. So what XGS Lab does is it's a flexible grounding software. You can also evaluate AC interference concerns such as transmission lines next to pipelines, how much induction you may have. It's flexible software that allows you to do complex grounding system analysis for various systems. The more accurate you can be on your modeling, the more you can match reality. And that's our ultimate goal, is to create a virtual twin of what the physics is of a fault and how that's going to translate in your grounding system. When we're actually performing tests of these sorts of systems, you have to be able to have equipment that's either sensitive enough to detect the millivolts or less, depending on how much current you're actually injecting, or very powerful equipment. So there are different testing outfits that have different processes for validating grounding system design. And I think that's just highly recommended in any sort of engineering process, is to validate the design and perform engineering measurements after the construction to verify that, first off, it was constructed to design, and that the data going in provides accurate data going out.
Thank you, David, for a great job. We appreciate everybody joining today, and check out the newsletter for the upcoming. Obviously, we're going to have more presentations of this type in the near future. Good day to all.
Thank you.
Thanks.